In this video, we're going to talk about complex roots. If you have a polynomial that has real coefficients, then you have the following. You have the following theorem. If a plus bi, a and b are real numbers, then a minus bi is also a root of the same polynomial. Again, this is only true if the coefficients of the polynomial are real numbers. They can be rational, irrational, they just can't be complex. In such a polynomial, if 3 plus 4i is a root, then so is 3 minus 4i. And for the record, if 3 minus 4i is a root, then 3 plus 4i is another root. They come in what's called conjugate pairs. Suppose that p of x is 3x squared minus 4x plus 2. We can use the Carte's rule of signs to determine some condition on the rational roots. Real roots. This is understood to be positive. There's a sign change here and here. So when it comes to positive real roots, there were 2 sign changes, and you can always go down by 2. There will be either 2 or 0 positive real roots. Now we look at p of negative x, which is 3x squared plus 4x plus 2. The first term is understood to be positive. There are 0 sign changes, so there are 0 negative real roots. So we won't bother to check for them. Let us find the roots. Since it's a quadratic, we can use the quadratic formula. X is equal to negative b plus or minus b squared minus 4 times a times c all over 2 times a. And we plug in the a, b's, and c's. A is 3, b is 4, c is 2. So b goes here and here, a goes here, and c goes there, and a goes there. And we get what we get. We get negative 4 plus or minus. This is 16, and this is 24. 16 minus 24 is negative 8 over 6. So we're going to get 2 complex roots. That is, we're going to get 0 negative real roots, as we already knew, and 0 positive real roots. Now, the square root of 8, square root of negative 8, well, the largest number that I know the square root of that goes into negative 8 or into 8 is 4. This is 4 times 2 times negative 1. All over 6. Negative 4 plus minus. I know the square root of 4. I actually know the square root of negative 1. And I do not know the square root of 2. All of this gets divided by 6. I can factor out a 2. I get negative 2 plus or minus I square root of 2 over 6. The final answer will be that over 3, because 2 goes into 6 3 times. So we got 2 complex roots. And notice that they came in complex conjugate pairs. This here is a symbol or a representative for 2 numbers. Negative 2 plus I square root of 2 over 3, as well as negative 2 minus I square root of 2 over 3. 2 numbers. Now, suppose you were given the polynomial x squared plus 16 equal to 0. That means that x squared is negative 16. And after all, that's what you add 16 to get 0. Or you add 16 to that number to get 0. So x must be plus minus the square root of negative 16, which is plus minus 16 times negative 1. As long as both of these are not negative, you can take the square roots separately. I know the square root of 4, and I know the square root of negative 1. These are the 2 answers. X can equal 0 plus 4i, and x can equal 0 minus 4i. Plus 4i minus 4i. Complex conjugates. They come in pairs. Suppose you had x cubed plus 8 equals 0. X cubed plus 8 is equal to 0. Well, that means, well, this has to be negative 8. I don't care what I just circled. There's only one number to add 8 to get 0, and that's negative 8. In other words, if I ask you to fill in this box, you would put in negative 8. So that must be negative 8. Well, I know what real number to cube to get negative 8. It's negative 2. So what I just learned was that one of the factors of x plus 8 is x minus that root. It's x minus that number, which becomes plus 2. What's the other factor? Keep in mind that 8 is 2 cubed. Well, if you have a cubed plus b cubed, this factors to a plus b times a squared minus ab plus b squared minus ab. And in our case, a is x and b is 2, because 8 is 2 cubed. So b is 2. So we get, just going to read this off, Instead of writing a, I'm going to write x, and instead of writing b, I'm going to write 2. It's a squared minus a times b, I wrote b first, plus b squared. Okay, so now we're down to a quadratic. Can you think, there's an understood one here. Can you think of 2 numbers that multiply out to 4, but add up to -2? Personally, I can't. Well, C is 4, B is -2, A is 1. So X is -B plus minus square root B squared minus 4AC all over 2 times A. My job is to plug in the A, B's, and the C's. B is -2, okay. A is 1, C is 4, A is still 1. So I get +2 plus minus 4 minus 16, negative again. And this time we get -12 under the radical. So this is equal to 2 plus minus the square root of -12 over 2. The only number that I know the square root of that goes into 12 is 2. Is 4. 4 times -1 times 3. They multiply out to -12. 2 plus or minus. I know the square root of 4. I know the square root of -1. I have no idea what the square root of 3 is over 2. This becomes 1 plus or minus 1i square root of 3 over nothing. It's just 1 plus or minus I times the square root of 3. There it is. That is, if you cube this number, any one of those two numbers, this is two numbers, if you cubed it, and then you add 8, you won't believe it, but you'll get 0. If you cube this number, and then you'll get -8. And then, of course, when you add 8, you'll get 0. Suppose you have x squared minus 4x plus 4 equals 0. Well, there's a 1 here. You know what? Half of that number is -2. And when I square it, that constant is right there. That is, the left side is a perfect square. It's x followed by half of that number. This is x minus 2 times x minus 2 equals 0. So either that's 0, which is when x is 2, or when that's 0, x equals 2. X equals 2 is a double root. It isn't just one root, because a quadratic has to have 2 zeros. A cubic must have 3 zeros. An nth degree polynomial must have n roots. Like in all the cases, some can be real, some can be complex. Some can be doubled. We count them twice. Now, let's change to a different topic, or a different type of problem. Find a polynomial with the following conditions. You want it to be degree 3 with 2 roots being, say, 3 and I. Now, when I say find a polynomial, I mean with real coefficients. The coefficients are real numbers. In case that's been bothering you, x squared, or let's say x cubed, x squared, x and a constant. The coefficients have to be real numbers, like 2/3, or the square root of 7, or -pi, plus, I don't know, e to the 3rd power. However, if you have 2 plus 3i times x cubed. I mean, already it's not a polynomial with real numbers, with real coefficients. These numbers, these coefficients are real numbers. You may not like some of them. You may not like any of them, but they're real numbers. That's a complex number. I do not guarantee you that we will have, if we get a complex answer, that they'll happen in pairs. I promise nothing about the roots of this polynomial. Plus 7x is equal plus minus 2i is equal to 0. I promise nothing about this. Here, I promise that if there are complex roots, they will happen in conjugates. So above, when I say find the polynomial, I mean with real coefficients. Okay. So I know that 3 is a 0. So p of x has to have x minus 3. And remember, this is 0 plus I. So 0 plus I must be a factor. That is x minus I. And another factor must be 0 minus I, which is negative I. So x minus negative I, which is x plus I, must be a factor. What makes this 0? 3. What makes this 0? I, which they gave us. What makes this what makes that 0? Negative I. Oh, I is a complex number, so we also have to have the conjugate as a 0. Now, it's easier to first multiply the conjugates. This is just going to be x squared plus, there's an understood 1 here, 1i, plus 1 squared. Now we distribute. X times x squared, x times positive 1, negative 3 times x squared, minus 3. There are no like terms. There is your polynomial. It has 3 roots. 3i, the 2 given ones, and the one that we figured out by knowing that complex roots occur in conjugates. Let's play the same game again. The degree of the polynomial is going to be 3, and 2 zeros or roots are 4 and 3 plus 2i. Well, the instant you have a complex root, that means you have a second complex root. Oh, just want to look at one thing in the last problem. What you can do right here is multiply this answer by any scalar you like 7 or 2 or 9. It's not going to change the fact that this is a 0 at 3 and those are zeros are plus or minus 1. So you can have ax cubed plus ax minus 3ax squared minus 3 for any choice of a that you like. If you happen to like 3, fine. You could multiply by 3. 3x cubed plus 3x minus 9x squared minus 9. This polynomial, it has 0, I, and negative I as its roots. If you don't believe that, plug in I. See if it works. Maybe I'm making this stuff up. Okay. So here, we're going to have a polynomial, any constant you want, One root is 4, so it's going to be x minus 4. Another root is 3 plus 2i, so it's going to be x minus 3 plus 2i. And another root is 3 minus 2i, so it's going to be x minus 3 minus 2i. The best and easiest way of doing this is to realize that that's x minus 3 minus 2i. Because you have to take away 3 and you have to take away 2i. Now here's the beauty. This is also x minus 3 plus 2i. These two are complex conjugates. So we have a times x minus 4. And when you multiply complex conjugates, you get the real part squared plus the imaginary coefficient squared, which is 4. So we get some number of our choice times x minus 4. And when I FOIL that out, get x squared minus 6x plus 9 plus 4. 9 plus 4 is plus 13. A times, distribute the x. You get x cubed minus 6x squared plus 13x minus 4x squared minus 4x squared plus 24x minus 52. This is A. You have x cubed. You take away 6x squared. You take away 4 more. You took away 10x squares. And then you have 24x. And you take away 52. And if you notice, there's something that I didn't cross off. Oops, 13x plus 24x is 37x. That's why you cross things off. So in the end, if there's nothing left over, if there's something left over, you didn't deal with it yet. And again, pick some number for A. I'm not suggesting you write A. You can put the number 7 right from the beginning. My advice is to put no number. Okay, so you have 7x cubed minus 70x squared plus our 259x minus 364. Okay, 210, 259. This polynomial, it has 3 roots. It has 4, 3 plus 2i, the given 2, and 3 minus 2i, the one that we had to figure out on our own. Let's do this again. Suppose the degree of the polynomial with real coefficients is 4, and some roots are 1 and say 1 plus I, where 1 is a double root. Okay, so the polynomial is going to have 1 as a root 2 times, x minus 1, x minus 1. And it also has a complex root, 1 plus I. So it's going to have x minus 1 plus I. And if 1 plus I is a root, then 1 minus I will be a root. So you have x minus 1 minus I. The first two multiply out to x squared minus 2x plus 1. And the next two, you should really be able to do this. It's x minus 1 in brackets minus 1. minus I, excuse me. This is an I. Minus I. And here you have x minus 1 plus I. You have a real part minus 1i. The same real part plus 1i. That's going to multiply out nicely. You're going to get x minus 1 squared plus the 1 from the I squared squared. So you have x squared minus 2x plus 1. When you square that, you get x squared minus 2x plus 1 plus another 1 is plus 2. Now, if you like, you can think of this as, say, u. If you had u plus 1 and you multiplied by u plus 2, you'd get u squared plus 1 plus 2 is 3u plus 1 times 2. So we can do the same. You're going to get x squared minus 2x squared, that's the u squared, plus 3 times u, x squared minus 2x, plus 2. Well, when you square that, you get x to the 4th minus 4x cubed, plus 4x squared, plus 3x squared, minus 6x, minus 3, plus 2. You get x to the 4th minus 4x cubed. Those seem to be the only x cubes. 4x squared plus 3x squared, that's 7x squared, minus 6x, plus 1, minus 1. Minus some silly error. This is a polynomial that has 1 as a double root, that is 1 and 1, and it also has 1 plus I, and then to make sure we have real coefficients, it has 1 minus I. Suppose you were asked to find the roots of this polynomial. P of x is, say, x to the 4th minus 6x cubed plus 13x squared plus 6x minus 104. You're asked to find these roots. Looks like fun. Well, you have one sign change or a second sign change, still only 2. You have 3, you can always decrease by 2, 3 or 1 positive real roots. There won't be 2 real roots, there won't be 4, there won't be 0, either 3 or 1. Now to find negative roots, replace x with negative x. You're gonna still get x to the 4th plus 6x cubed plus 13x squared minus 6x minus 104. One sign change, one sign change. You can't go down by 2 if you're at 1. 1 minus 2 is negative 1. What will it mean to have negative 1 real roots or real negative roots? You will have 1 negative real root. I guarantee you of that. So just for the record, what might we have? And we have positive and negative and complex. Well, when it comes to positive roots, we either have 3 or 1. When it comes to negative roots, we're guaranteed to have 1. In total, we have 4. Well, 3 plus 1 is already 4, so we have no complex roots. 1 positive, 1 negative, that's 2 roots. The other 2 will be complex. Okay. So now, how might we go about finding these real roots? Let me just get rid of this. How do we go about finding it? Actually, I want to keep that table up here. Plus, minus, complex. You can have 3 or 1. And definitely 1 negative. So, we have that. That is, we have to find a negative real root. And if we find 2 positive real roots, go and find the third one. So the rational roots test says to write all numbers that go into 104, write all numbers that go into 1, which are plus minus 1, and divide all combinations from the top and the bottom. Well, 1 goes into 104. It's an even number, so 2 goes in. When you add the digits, you only get 5. 3 doesn't go into 5, so 3 doesn't go into that number. 4 goes into that number. 5 doesn't. The divisibility test for 6 is 6 only goes into a number if 2 and 3 go into the number, but we bypass 3. Does 7 go into this number? 1, no. Does 8 go into this number? 8 into 104. 1, 2. Goes in 13 times. So, in fact, what we could do and should do is 1 went in 104 times. 2 went in 52 times. 4 went in 26 times. 7 did not go in. 8 did not go in. 9 doesn't. 10 doesn't. Oh, 7 did go in, excuse me. 7 went. 7? Did 8 go in? 52. Yeah, sorry. 8 was the one that went in 13 times. 9 doesn't go in. 10 doesn't go in. 11 doesn't go in. 11 times 9 is 99, 5 left over. 12 doesn't go in because 3 didn't go in. And 13 does go in. And that's where we stop because I already said 13. Only because I didn't write it so neatly. Let me write it again. The numbers that go into 104 are plus minus 1 and 104 and plus minus 2 and 52. I think you should write them in those pairs. Plus minus 13, plus minus 26, plus minus 26, plus minus 52, and plus minus 104. Now the only numbers that go into 1 are plus minus 1. Now if you take any one of these numbers, pair of numbers, and you divide them by plus minus 1, you get back that same number. In other words, if you had plus 4 over plus 1, plus 4 over negative 1, negative 4 over plus 1, or negative 4 over negative 1, you get 4, negative 4, negative 4, 4. That is, you only get back plus minus 4. Okay, so when we divide all the top numbers by all the bottom numbers, we actually end up with these numbers. 1, 2, 3, 4, 5, 6, 7, 8, 16 different possible rational roots. I would use the rational root test. Let us test for number 1. It's 1. I'm copying down this polynomial up here. Just the coefficients. It's 1x to the 4th, 6x cubed, 13x squared, negative 6x, and the constant is negative 104. Always at the beginning, you put a 0. You add, then whatever you get, you multiply by this number, and you put it up there. Preferably a 1. No x. You add, you get 7, multiply the 7 by 1, put it here. You add, you get 20, multiply the 20 by the 1 in the front, you get 14, multiply it by the number in front, you get 14. And you want to get 0. We didn't get 0. So let's try 2. Let's see if 2 is going to work. Let's see if 2 works. So we have a 2 in front. 1 plus 0 is 1. 2 times 1 is 2. You add, you get 8. Multiply it by the number in front. Get 29. 2 times 29 is 58. You add, you get 52. When you multiply 52 by 2, you get 104, which is 0. That means that this polynomial, x to the 4th minus 6x cubed plus 13x squared plus 6x hold on a second, minus 104. I have minus 6x. Okay, minus 6x. We now know that x minus this number is a factor. And the other factor will be, since it was x to the 4th, we go down 1 to x cubed plus x squared plus x plus the constant. The other factor is x cubed plus 8x squared plus 29x plus 52. Now, I should have crossed out. Okay, so now let's find the possible rational roots. 52 and 1. 52 is smaller. The numbers that go into 52 are plus minus 1, plus minus 52. 2, 26. 3 doesn't go in. 4 goes in 13 times. 5 doesn't. 6 doesn't. 7 doesn't. 8 does not. 9 doesn't. 10 doesn't. So it looks to me like these are the roots. Let me just move them closer to one another. Plus minus 4, 13, 26, and 52. Those are the possible rational roots. Now, for example, if 17, let's pick a number on here, 13. If 13 was not a rational root for the beginning polynomial, it won't be a rational root here. And I'm pretty sure we tried 1. Now, just because 2 worked doesn't mean we should cross it out, because maybe 2's a double root. So the synthetic division is going to be 1x cubed, 8x squared, 29x's, and a constant of 52. Now, these numbers are all positive. Okay, in other words is, if you plugged in a positive x, when you cube that number, is positive. When you add on 8x squared, it'll be positive. When you add on, you'll be adding more, that is. 29x, you'll be adding on more. And then you add on 52. This is never going to be 0. So it's always going to be more than 0. So basically, we can argue, hey, none of the positive numbers are going to work. So, I don't know, maybe we'll try -1. Put 0, bring it down. Multiply this number by -1. You add, multiply it by -1. You add, multiply it by -1. You don't get 0. So, -1 is gone. Let us try -2. Let us try -2. 0. 1 times -2 is -2. You add, you multiply, you get 17. Ooh, not enough. -34. That's not 0. You want to calculate what it is and spend time? Fine. But I'll tell you this, 52 plus -52 is 0. So 2 did not work. Let us, -2. Let us try -4. Add, multiply, add, multiply, add. Ooh, multiply. Actually, I thought that wasn't going to work. Multiply. We got 0. That is, our polynomial is x minus 2. Now, I just learned how to factor this. It's going to be x minus that number, because -4 was a 0, so it becomes x plus 4. This is x squared plus x plus 13. So x squared plus 4x plus the number 13. Okay, now let's see what's going on. Somewhere we said that we'll have either 3 real roots and 3 positive roots and 1 negative, or we'll have 1 positive and just 1 negative. Well, let's see. We found our negative right there. We found -4. Okay, so we found the 1. So either there's going to be 3 positive real roots or just 1. Well, we found 1, 2. So we can use the quadratic formula to figure out what the other 2 roots are. Okay, so let us find the roots of x cubed plus 4x plus 13. X squared, I meant, plus 4x plus 13. So a is 1, b is what x is being multiplied by, and c is the constant. And a is what x squared is being multiplied by. So x is negative b plus or minus b squared minus 4 times a times c all over 2 times a. And like always, we plug in the values. B is 4, b is 4, a is 1, c is 13, and a is still 1. So we get -4 plus or minus, 16 minus 52. That's going to be negative. So we're going to have 2 complex roots. 52 minus 16 is 36. So we get negative 36, which is a nice number because I know the square root of 36 and I know the square root of the negative 1. Factor out a 2, you get negative 2 plus or minus 3i over 2. The 2 naturally cancels out, and you get your 2 complex roots. So the instructions are to find the roots. Well, the roots are negative 2 plus 3i from here, negative 2 minus 3i from there, and earlier on we found out 2 and negative 4. 2 and negative 4. 2 and negative 4. Those are the 4 roots of that 4th degree polynomial. And there better be 4. A 4th degree polynomial has 4 roots. Some are complex, but there's 4 of them in total. 4 roots. And remember, sometimes they can be, say, negative 2 plus 3i and negative 2 minus 3i and just the number 7. But this 7 is a double root. That is, one of the factors will be, or 2 of the factors will be x minus 7 times x minus 7 times x minus negative 2 plus 3i and x minus this root, x minus negative 2 minus 3i. This completes the section on complex roots.